This is lesson 5.2, the mole. So this is what our unit is about, is the mole. This is going to tell us about chemical composition. The mole is essentially a group of particles, and it's just a word that's going to count a group of particles. So just like the mole, we have other words that describe a specific number. So the word dozen refers to 12 somethings. 12 donuts, 12 roses, or 12 eggs. We also have some other words that represent numbers. In a ream, there are 500 sheets of paper. In a pair of socks, we have 2 socks. A gross, it is 12 12s, so 12 times 12 gives us 144. Avogadro's number is 602 000 000 000 000 000 000 000 000 602 with 21 zeros after it. That's a lot of zeros, right? We don't want to sit there and count out atoms to this many. We want to be able to group them together. And so that's what Avogadro's number is. Amedeo Avogadro developed this. And so in scientific notation, it is 6.02 times 10 to the 23rd. Because remember, I said there's 21 zeros. So we're moving our decimal 21 places to get these are really bad here. So that's 21 places, but we want something less than 10, greater than 1 in front of our decimal. So 22, 23, and that's how we get 6.02 times 10 to the 23rd. Now we can call 6.02 times 10 to the 23rd Avogadro's number or the mole. Both of those are used interchangeably. So how big is a mole? Let's just think about it like this. If the average human heart beats 72 times per minute, how old would you be in years if your heart beat a mole of times? Okay, so in this problem, we are given a mole of heartbeats, which is 6.02 times 10 to the 23rd heartbeats. And we want to find the number of years. Okay, this here, 72 times per minute, is going to be a conversion factor. Okay, so we're going to start with what we're given, 6.02 times 10 to the 23rd heartbeats. Because we always start with what we're given. But we don't want heartbeats, we want years. So we have this conversion factor, 72 times per minute are heartbeats. So we can write this 72 heartbeats, because we want heartbeats to cancel out per 1 minute. So then we can cancel out heartbeats. Well, we don't want to know minutes, we want to know years, so we got to convert away from minutes. So in 1 hour, there are 60 minutes. Well, we don't want hours either. So in one day, there are 24 hours. But we don't want days either. We want years. So in one calendar year, there are 365 days. So then days cancel and we're left with years. So what you're going to do is you're going to multiply 6.02 times 10 to the 23rd times 1. And in your calculator, you're going to put in 6.02. And on most people's calculator key, then you're going to press the second key. And then there should be a capital E like this. The E is your times 10 to the caret. Saves you a little bit that you have to put in, and it also saves you from having to put in your parentheses. So 6.02 e to the 23rd. That's all you have to put in for this here. Multiply that by 1, which is still going to be 6.02 e to the 23rd, 6.02 times 10 to the 23rd. Divide it by, open parentheses, 72 times 60 times 24 times 365, and then equal it, and you should get 1.59 times 10 to the 16th years. Now I rounded this. I have 2 decimal places here, so I rounded to 2 decimal places here. So this is our final answer. This is just to give you an idea. Our heart beats 72 times per minute. Well, if my heart was to beat a mole of times, it'd be 1.59 times 10 to the 16th years. Probably none of us are going to live to that age in order for our heart to beat a mole of times. So that just tells you how big this number is. So why is Avogadro's number so big? Avogadro's number represents the number of particles, and these particles in chemistry are extremely small. And so scientists needed an easy way to count such a huge number of them. And so we group them together, 6.02 times 10 to the 23rd. Well, what are these particles that Avogadro's number or the mole represents? Those particles can be, aluminum is an atom. It's a single type of atom. So a single element by itself, nothing else. I'm actually going to back this up. It's still a single element. I just wanted to format this a little bit better for you. So in your first column, you have aluminum, ammonia, and you have sodium chloride. I have iron chloride, but these will all work the same way. So we said that this is a single element, just one by itself, not a single type where you have 2 of the same kind bonded together. Atoms, we're going to abbreviate AT. Molecules is going to be a covalent compound. And remember from our last unit, covalent compounds are a nonmetal and another nonmetal bonded together. Or it could be a nonmetal and a metalloid. We're going to abbreviate molecules MC. And then formula units is for ionic compounds. And so in our ionic compounds, we have a metal and a nonmetal. So even though identifying ionic and covalent was in our last unit, those are things that are going to carry with us for the rest of the year. Formula units, you may have guessed it, is going to be abbreviated FU. Okay? So at the bottom of your page, you have this diagram. I want you to take a look at it and see if you can label them as atoms, molecules, or formula units. Welcome back. Let's label these. Lithium, it's a single element, so this is atoms. Cu bonded to two chlorines, well, we have a metal, so this is going to be Fu, formula units. We have two hydrogens bonded together. Both of those are non-metals, so that's going to be a molecule. Magnesium bonded to carbon and three oxygens. That's an ionic compound, so it's going to be formula units, Fu. Sodium bonded to chlorine. Again, we have a metal, so it's ionic, formula units, Fu. Two oxygens bonded together. Both of them are non-metals, so we have a molecule. Iron, single type of element, single element by itself. So this is going to be an atom. Water, H2O, all of it is non-metals, so this is going to be a molecule. And then carbon bonded to two oxygens. Again, all of it is non-metals, so that's going to be a molecule. I want you to note that molecules are covalent compounds and formula units, when we have our ionic compounds, are made up of atoms. Okay? So even though we are grouping these together, the molecules and formula units are still made up of atoms. And that's going to be important for what we look at next. So, in one molecule of H2O, of water, how many oxygen atoms do we have? Well, we don't have a subscript there, so that means we have one. Hydrogen atoms, we have a subscript 2, so we have 2. So how many atoms do we have total in one molecule? We have 3. That was fairly simple. So now, if you have 1 mole of water, we need to set this up a little bit differently. So in 1 mole, go back. So remember we said that 1 mole equals Avogadro's number, 6.02, times 10 to the 23rd. And this can be atoms, or we can have 6.02 times 10 to the 23rd molecules, or 6.02 times 10 to the 23rd formula units. It's whatever the representative particle is. It depends on if we have just a single element, if we have covalent compounds, or if we have ionic. So in 1 mole of water, how many molecules do we have? Well, 6.02 times 10 to the 23rd molecules of water. Okay, so now we know how many molecules we have. So we're given 6.02 times 10 to the 23rd molecules of water. We want to 1 mole of water, how many oxygen atoms we have? Well, we know in 1 molecule of water, there is 1 atom of oxygen. So this is just going to be 6.02 times 10 to the 23rd atoms of oxygen. And again, it's very, very, very important to label your numbers so you know what you're referring to. Okay? Now we can use the same setup now to figure out our number of hydrogen atoms. Raise my answer. Erase that. So now, in 1 molecule of water, we have 2 atoms of hydrogen. So these cancel off. So now we're going to take 6.02 times 10 to the 23rd, multiply it by 2, and you should get 1.20 times 10 to the 24th. And this is going to be atoms of hydrogen. So for our third one, there's a couple of ways that you can work this. You can either add 6.02 times 10 to the 23rd plus 1.20 times 10 to the 24th, or you can change this yet again, and we said that there is a total of 3 atoms. So in 3 atoms, 6.02 times 10 to the 23rd times 3 should give us 1.81 times 10 to the 24th, and this is just atoms, total atoms. So we're just going to label it atoms. Okay. The problem at the bottom of page 5 and the top of page 6 is going to follow the same process. So remember, if it asks for in 1 mole, you need to follow this. It might be helpful to look at this part, try to figure that out on your own, but this is the sort of thing it's going to look for. And one other thing I just wanted to note is that that practice problem at the bottom of page 5 is zinc nitrate. Okay? We have 1 zinc atom. No subscript, so it's just 1. This 2 is telling us that we have 2 NO3s. And we're going to just multiply this times everything on the inside. So we have 1 atom of zinc. We have 2 atoms of nitrogen. And 2 times 3 is 6 atoms of oxygen. Okay? So go ahead and work through those. Do all of the problems on page 5 and the one on the top of page 6. Make sure that you understand this. It's going to continue to build. So you want to make sure that you understand this. Come in and ask me questions if you need help. Thanks for stopping by. Have a great day.